much. And in particular, thanks a lot to the organizers for inviting me to speak in this really very interesting meeting and to present some ongoing work, hopefully to appear soon, with Song-Ju Lee and Wolfgang Lerche on the infinite distance limits in F-theory compactifications in the complex structure moduli space. And this work will be on the first step on elliptic K3 surfaces. And in the broader introduction, I will also summarize to those who have not followed this field some previous work with these collaborators. So as in the previous beautiful talk by Thomas, and as it was discussed, the Swampland program is a development in the recent high energy literature, which tries to identify criteria in order for an effective field theory to arise as the low energy approximation of a consistent quantum gravity theory. And I think we all agree that if successful, this program would have tremendous impact on different areas of fundamental physics. In fact, let me remind us that the recent burst of interest in this is at least partly motivated by our endeavor to understand early universe cosmology. Namely, one of the questions that we try to understand in early universe cosmology is how far a scalar field can travel in the moduli space within the range of validity of an effective field theory. This question is of particular importance when we think about properties of inflation. For example, can we have large field inflation and therefore a significant amount of primordial tensor modes, for example. And it was a very physical question like this, which then in fact motivated us in string theory to take this question seriously and rethink what possible constraints could arise in the moduli space of a theory as underlying the one of early universe cosmology. So this is just one example where we have indeed a direct physical question in mind that motivates this line of research. Other important questions of fundamental importance are, for instance, whether a quantum gravity theory could have viable matter-stable de Sitter vacua. We heard about this already yesterday in Benner's interesting and important talk. Another question, can we have ADS vacua within a quantum gravity with scale separation, so a separation of scales between the KK scale and the ADS scale, and many other questions of this type, but also questions that are more to the heart of directly particle physics. Are there constraints on the charge spectrum in a theory? So when we think about modeling beyond the standard model physics, are there any additional constraints that we need to take into account, or does anything go in a quantum gravity theory? Are there constraints on low energy supersymmetry breaking, and so on and so forth. So this program, even though sometimes formulated in a very mathematical way, is clearly heading towards, or at least aiming to address very important physical questions. So since the questions are so hard, it is difficult to make progress without any assumptions. And in fact, this Swampland program is known to make assumptions of two types, either in a bottom-up approach or in a top-down approach. In the bottom-up approach, one could try to find general principles to hypothesize on the existence of general principles, which every viable quantum gravity theory should encompass. This line of research then does not make any direct assumptions about the fundamental description of quantum gravity, but it tries to come up with general principles based, for example, on consistency with what we think to know about black holes or other hopefully accepted principles in high energy physics and gravity. This bottom-up approach is rather broad in scope because it's not limited to, say, string theory or loop quantum gravity, or you name it, but necessarily it is oftentimes speculative and heuristic in its arguments. And this is what has produced by now an ever-growing web of conjectures, which, even though conjectural, nonetheless exhibit a remarkable amount of interrelations and logical connections. And this is just a small, very small subset or subweb of the web of conjectures which are formulated in this bottom-up approach. In a top-down perspective, we can make concrete assumptions about the actual quantum gravity theory, what the actual microscopic formulation should be, and try to deduce consequences for the resulting effective field theories. And this, while less general, has the clear advantage that it allows for precise statements within a given concrete computational framework. And for us, this framework in this talk will be string theory. And in the context of string theory and string compactifications, this approach, in addition, offers interesting relations to mathematics, as I already hinted to at the beginning. Namely, it promotes the questions: which properties of string compactifications guarantee the conjectured Swampland criteria, whichever these are? And we just heard in Thomas's very nice talk for investigations in this direction in a particular area. So to summarize, for me, the Swampland approach would be consisting in these three pillars, or consist of the steps in between them. On the one hand, we can try to come up with quantum gravity conjectures based on general reasoning in a heuristic way, oftentimes. These arguments would then make predictions for what should happen in a concrete quantum gravity, such as string theory, and in turn, looking at what happens in well-defined theories, which we believe string theory is, would allow us to test the original conjectures and maybe develop them further. But there is then also this connection to mathematics, namely to check whether a particular general principle is then actually realized in mathematics, in string theory, requires the use of mathematics, oftentimes of high-class mathematics, in order to prove the statements. But we can also turn tables round, and if the mathematical proof is not available, can translate the conjecture about the physics into a conjecture about the mathematics, namely by conjecturing that, for instance, the mathematics of string compactifications should always be such that it guarantees certain of these Swampland criteria to be realized whenever we apply it. So this opens up a nice new arena for contact with mathematics, that we try to abstract and translate some of these Swampland ideas into statements that must then hold in generality for the mathematics underlying, in this case, string theory compactifications. So before I come to the main part of my talk, I would like just to advocate this point of view in one example. Namely, one example would be the conjecture of completeness in quantum gravity. What is this conjecture? Well, first, in a usual quantum field theory without gravity, as we all know, not every charge must actually correspond to a physical particle. The key example being even pure Yang-Mills theory, where apart from the adjoint representation, you would have no representations whatsoever. The completeness conjecture, however, postulates that in a quantum gravity theory, such behavior is unacceptable. In other words, every charge in the weight letters of a, say, gauge theory coupled to quantum gravity should in fact correspond to a physical state. So this is a conjecture based on, again, black hole considerations or other heuristic arguments. So let us apply, just as an example, this conjecture to theory in 6 dimensions with 8 supercharges. So 6D n equal 1,0 supergravity theories. In such theories, as we know, we have a dynamical 2 form, which couples to 1 plus 1 dimensional objects, the strings, the in general non-critical strings of the 6-dimensional theory. And while in a general supergravity, these strings may or may not be realized as physical objects, according to the quantum gravity conjecture I just cited, all of them, the entire charge letters should in fact be populated by such physical strings. These physical strings being a 2-dimensional quantum field theory in their own right, they must be well defined in order for the entire theory to be well defined. So according to this probe argument, the 6-dimensional supergravity theory should be such that every such 2-dimensional probe, every such string which probes the 6-dimensional supergravity is well defined. In particular, it must be free of anomalies, or if anomalies are there, they must be cancelled by an inflow mechanism. And the theory must be unitary if it flows to a superconformal field theory, So these constraints on these defects, which by the completeness conjecture must be present, constrain the 6-dimensional theory beyond the usual constraints which one would have in supergravity. And this was used first in these papers and then a number of papers that followed in order to derive several such constraints. And just to give one example, one of the consequences of this is that in a 6-dimensional n equal 1,0 supergravity theory, the number of abelian gauge group factors is constrained. There is a sharp bound of 24. This refers to all n equal 1,0 supergravities. In particular to those with t equals 0 tensors. If they have at least one tensor or more, the bound is even sharper, namely 16, but the very sharp bound, including everything, should be 24. And this was derived in this paper by looking at precisely some of these consistency conditions of the spectrum of strings in such 1,0 theories. So this physics consequence, and this is now my main point, one can translate into a mathematical statement. Namely, suppose we engineer 6-dimensional supergravity theory in F theory, then we know that the rank of the abelian gauge group part is given by the so-called model Weil group of sections of the elliptic vibration. And the fact that we cannot have more than 24 such U1 gauge group factors would imply that the number of independent rational sections of an elliptic Calabi-Yau threefold, in other words, the rank of the model Weil group, must be bounded as well. It cannot be bigger than 24. And this is a new bound, which is new to the mathematicians. In fact, there are no statements in the mathematics literature to date what the upper bound for the rank of the model Weil group on a Calabi-Yau and an elliptic Calabi-Yau should be. And if this line of reasoning in the physics is in fact reasonable, then we would in this way produce a conjecture for the mathematics. And clearly, when such a conjecture is out there, it's interesting to try and test it, check or devalidate it. And in fact, there is a discipline of sports in mathematics, which is the record hunting for the number of sections in elliptic vibrations. And motivated by these considerations, we could show that the current record for such elliptic vibrations is in fact given by a rank of 10. These are certain Schoen manifolds. But clearly there's a lot of room here, so a lot needs to be understood more. So all this just as one example how these physics considerations and general constraints on the physics can be translated into also interesting conjectures, which might be interesting from a purely mathematical point of view. Now, the main part of my talk will be not about the completeness conjecture, but about the Swampland distance conjecture, which in many respects lies really at the heart of the Swampland program. Those of you who have followed the field know this very well. Let me nonetheless please take a couple of minutes to summarize this. The Swampland distance conjecture is the statement that in a quantum gravity theory with couplings, first of all the couplings should be dynamical, so they should be part of a moduli space. And second, this moduli space should allow for infinite directions with respect to the metric on moduli space in such a way that as we traverse an infinite path in the moduli space, the theory is such that in infinite number, a tower of states becomes massless exponentially fast. So more precisely, this is the situation for paths such that every, or between starting the endpoint, such that every path in between is of infinite length. So as we go to infinite distance in the moduli space, an infinite number of states should become light exponentially fast. And furthermore, it should be such that the order of proportionality in this exponential argument here should be constrained to be of order 1. This is part of the refined Swampland conjecture. And the region where the exponential decay of the particle masses starts, or in other words, the region that one first has to traverse before this exponential decay starts, this would be this blue region. This should also be only of length of order 1 or of diameter of order 1 in the moduli space. This would then be a part of this refined Swampland conjecture. And as I said, this distance conjecture is of fundamental importance in this whole within the swampland considerations, and it's of practical relevance, so to speak, for this whole field. For instance, one can use it to give an argument against the existence of metastable de Sitter vacua in asymptotic regions of moduli space. It's important to stress this. This makes no statement about what happens in the interior of moduli space, where, for example, KKLT or other constructions may or may not lie. The argument also gives intuition for the so-called ADS distance conjecture as another example, which would be the statement that as you take the cosmological constant in an ADS vacuum to 0, an infinite number of states should become light. And at least generally, it disfavors parametrically large field inflation asymptotically in field space. And both these constraints here are important. First of all, it's true only asymptotically. And this is something that, if anything, can constrain parametrically large field inflation. So here we make, again, the connection to my initial motivation of, say, early universe cosmology. Clearly, all this leaves a lot of room for concrete constructions, in particular constructions in the interior of moduli space. But by understanding what this region is better, in the context of the refined swampland conjecture, progress may or may not be able to be made here as well. So this is the conjecture that I'd like to discuss a bit more in this talk, the swampland distance conjecture. In fact, given the importance of this conjecture, it has received a lot of attention in the string theory literature already. Numerous checks and tests have been made in various corners of the string landscape. And in particular, I would like to highlight here the complex structure moduli space of type 2B compactifications, about which we just heard in Thomas's talk. In this case, the states which have been analyzed would be 4D n equal 2 BPS particle states. And as we see in this still very incomplete list, there has been tremendous progress in checking, or in fact almost proving, but for sure very testing the swampland distance conjecture in this regime of compactifications. And this line of research also has important implications for moduli stabilization of flux vector, as we just heard. And here again is an incomplete list of some of the recent papers. Good. So the swampland distance conjecture tells us that as we go to infinite distance in moduli space, this nature of the theory should change because an infinite number of states becomes light. But it does not tell us what the nature of these states is. And it also does not tell us what the nature of the theory that we encounter on the boundary at infinite distance is. So it could be, for example, like in a quantum field theory, that on some points on this boundary in moduli space, qualitatively new types of theories are waiting for us. For example, in quantum field theory, if we go to degenerations at finite distance, then we all know that there can be strongly coupled regimes where the nature of the theory changes completely, non-Lagrangian theories, and this entire zoo of interesting theories could occur. So it is therefore of importance not only to state that the theory degenerates at infinite distance, but also into what it degenerates. So we need to understand what is the nature of the particles that become light and what is the nature of the theory as we go to infinite distance. Do we find a qualitatively new quantum gravity theory at the infinite distance? Or do we, in a sense of duality, get back to something that we already know? This, as I said, is not answered by the swampland distance conjecture as such, but based on a representative set of frameworks that we analyzed, we in fact gave a refinement or a stronger version of the swampland distance conjecture, the emergent string conjecture, whose content is that we always get back something that we already knew. More precisely, the conjecture is, if a quantum theory of gravity admits an infinite distance limit, then the tower of particles should be of one of these two types. Either the tower of particles at infinite distance is the infinite tower of excitations of a unique asymptotically tensionless fundamental string, which emerges at infinite distance. In this case, the theory reduces to a weakly coupled string theory, and in fact, a weakly coupled string theory that we already know, say type 2 or heterotic weakly coupled theory at the infinite distance boundary. Or if there is no such infinite tower of string excitations, then at least the leading tower of massless states should have the interpretation of a Kaluza-Klein tower. So the theory decompactifies, say, from 4 dimensions to higher dimensions, and then we would have to reconsider again whether the theory undergoes a degeneration. Of course, this will stop at some stage in 11-dimensional M theory at the very latest. So this is the content of the emergent string conjecture. At infinite distance, we either have an infinite tower of string excitations, then we have a weakly coupled string theory, or we have a decompactification, then the interpretation of the particle tower was that as a Kaluza-Klein tower. And this statement has so far been confirmed in a number of non-trivial frameworks. In particular, in those frameworks that have been analyzed, it has been shown that all those cases which are not of decompactification type are such that there exists a unique, emergent, critical, asymptotically tensionless string on the boundaries of moduli space. And showing this heavily uses the geometry and in general the quantum geometry of the underlying string compactifications, and indeed a certain conspiration of in the geometry what happens at the infinite distance to make this possible. For instance, one can show this rigorously in all F-theory compactifications to 6 dimensions in the Kähler moduli space without any restriction. Similarly, in compactification of M-theory to 5 dimensions in the Kähler moduli space, and which would be the strong coupling version of type 2A to 4 dimensions on a Calabi-Yau, again, in Kähler moduli space. These are the vector multiplet spaces. For 4D n equal to hypermultiplet spaces, on the other hand, the statement has been scrutinized in this work, including also quantum corrections. Compactifications to 4 dimensions with n equal 1 include M theory on G2, as discussed by Xu, and 4-dimensional compactifications with n equal 1 in F theory, again in the Kähler moduli space, have been analyzed in these works. And of course, in 4-dimensional n equal 1, by the very latest, but also already for the hypermultiplets, quantum corrections play an important role. And indeed, they, to the extent that they could be analyzed, they conspire in order to guarantee this statement. So this almost concludes my overview, but let me just give you an idea of what happens once again, in case you haven't seen this. For example, consider compactification to 4 dimensions n equal 1 of F theory. In this case, the compactification space is the base of an elliptic vibration, so that's a complex threefold. And we can now look at the infinite distance limits in the Kähler moduli space. And first, we can look at those limits in the classical Kähler geometry, and thereby classifying the possible degenerations at infinite distance, we could show that one of 2 possible things happen. Either the theory is really a decompactification limit, or it is such that the compactification space must have a vibration structure such that the fiber of this compactification threefold is either a rational curve or a torus, so elliptic vibration or rational vibration, and such that the volume of this fiber shrinks to 0, with the consequence that wrapping a D3 brane on this shrinking fiber leads to a fundamental string in 4 dimensions, which could be either type 2 string or a heterotic string, type 2 in the case of a T2, heterotic in the case of a P1. And these then are precisely, this then is precisely the unique asymptotically tensionless critical string which appears at the infinite distance when the volume of this fiber goes to 0. So this would explain the emergent string conjecture in the classical theory. And in fact, in 4D n equal 1, this picture to the extent that we were able to analyze it, survives quantum corrections, in particular alpha prime corrections, first of all, to the Kähler potential. And in fact, these corrections are also needed in order to exclude certain regions which would lead to pathological behavior. So what would be the advantage? The advantage would be that in this picture, when going to infinite distance, we don't only observe that the effective theory, the original effective theory, breaks down, but we can actually see that a new type of regime starts at infinite distance. We go to a new type of duality frame. And in fact, this is a duality frame that is weakly coupled, so in which we can do computations. And by this line of reasoning, one can then, as a corollary, prove the weak gravity conjecture at infinite distance in these theories. In the present context, this goes as follows. The 7 branes, which give rise to the gauge sector in this F-theory compactification, become weakly coupled in these infinite distance limits. And the limits are precisely such that the dual heterotic string emerges as described, and the excitations of this heterotic string can then be proven to contain a sublattice, which in fact satisfies the weak gravity conjecture, in other words, whose charge to mass ratio is bigger than the charge to mass ratio of the relevant black holes in this theory. This involves a lot of input from the geometry, also from the black hole physics, and most importantly, again, from mathematics, because it is here that information about the nature of, say, the elliptic genus of these heterotic strings in 4 dimensions, and in general non-perturbative 4-dimensional n=1 settings enters. But all of this together then conspires to prove the weak gravity conjecture. And once more, this can be then even extended by quantum corrections, at least to first loop order, where we made a proposal for how the weak gravity conjecture would change. Okay, so this was my rather long introduction to why we're interested in the Swampland distance conjecture and what the current understanding is. But all these proofs or checks that have been done so far, be it in the Kähler moduli space or be it in the complex structure moduli space of type 2b compactifications on Calabi-Yau, they are always so far in the closed string moduli space. So it's a natural question and time to wonder if there can also be infinite distance directions in the brane and open moduli space, and if so, if the Swampland distance conjecture or its stronger version, the emergent string conjecture, are still viable in such situations. Well, as soon as one reads this first sentence here, one should certainly stop and realize that the question as such is not well posed at all, because as we all know, in general, we cannot sharply separate between open and closed moduli spaces. For example, if we consider F-theory, then the 7 brane moduli and the complex structure moduli of the compactification space, so to speak, together with the exodilaton, are of course known to unify into the complex structure moduli space of the entire elliptic vibration, say an elliptic fourfold for compactifications to 4 dimensions. So the proper way to phrase the task is to understand the physics and the mathematics of the complex structure degenerations, but in F-theory. So once more, for a complex structure of type 2b compactifications in various dimensions, this has already been done, but this is now a rather different setup. We're interested in the complex structure degenerations of F-theory and the mathematics, but in particular also the physics. And as a first step in this talk, we will be looking at probably the simplest case, F-theory in elliptic K3 manifolds to 8 dimensions. And we will take 3 related viewpoints. First, in a PQ brane picture, we will argue that these infinite distance degenerations lead to either recoupling limits or affine or more generally loop algebra extensions of the theory. We will then relate this to the algebraic geometry of semi-stable degenerations and explain how this PQ string picture is recovered in the theory of Kulikov models and their Weierstrass realizations. And we will give a physical interpretation, which will be backed up by duality with the heterotic string. So these are the 3 types of steps, which will also structure the remainder of my talk. And the main proposal in this paper to appear is that apart from general recoupling limits, the complex structure infinite distance degenerations for F theory on elliptic K3 can be characterized as follows. Physically, once more, they correspond to degenerations where some of the 7 branes, PQ branes, start realizing a loop algebra. So to this extent, it is justified to think of these infinite distance degenerations as degenerations in the brane moduli space, as this has to do with the formation of certain bound states or configurations, not bound states, configurations of branes. Geometrically, they can be understood as semi-stable degenerations of Kulikov type 2 or 3, which are obtained by blowing up non-Kodaira fibers in codimension 1. And we will recover these states from this geometric picture. And the interpretation of the tower of states is that of a dual decompactification limit, namely either decompactification from 8D to 10D. This would be, examples of this are the type 2 Kulikov models, or from 8D to 9D, this is what happens in the type 3 models. And all of this has to be then supplemented in addition by the recoupling limits, which I will not discuss in too much detail. So together with the recoupling limits, this is again in agreement with the string, with the emergent string conjecture. And my main point, so to speak, will be that this complicated looking type of tower that one gets in these Kulikov models indeed have an interpretation as a Kaluza-Klein tower, thereby realizing a decompactification limit. So this should hopefully clarify the physics at these infinite distance points, at least for the general class of F theory on elliptic K3. This will be the main proposal. And now we'll go, as I said, in these 3 steps. First, the PQ branes, then I'll go to the I'll move on to the language of degenerations, and then comment also on the heterotic dual. So as a reminder to all of us, we are thinking in terms of F theory with 7 branes. The 7 branes are general PQ 7 branes. These are those PQ branes on which a PQ string, so a bound state of P fundamental and QD1 strings can end. And of course, the hallmark of these 7 branes in F theory is that they backreact on the geometry. They induce a monodromy, an SL2Z monodromy on the general SL2 background of type 2B string theory, in particular, when we consider a PQ brane and encircle it by an RS string, then as we go back, the RS string will come back to new object, which can be computed in this way with the help of this monodromy matrix that we can read off from the labels P and Q. This, of course, is all ancient knowledge. And it is also ancient knowledge that stacks of these types of PQ7 branes then lead to enhanced non-abelian gauge symmetry in 8 dimensions. The only such symmetries could be of AD and E type, which corresponds to configurations of these coincident type of branes. It suffices here to take a basis, so to speak, or generating set of 3 PQ branes as listed here. And for each of these configurations, one can then compute the monodromy, or in turn use the monodromy to deduce what type of Lie algebra is realized. Now, important for us is that there is, however, a second type of enhancement, namely the enhancement of affine type or of general loop type. This was discussed in this classic paper, and it is the following statement. If we start with an EN type gauge symmetry, then we can enhance it to an affine algebra, an affine Lie algebra, by the addition of just a single brane, the brane of PQ type as given here. In other words, if we consider this original EN configuration and let it collide with a 3,1 PQ brane, then the combined monodromy can be computed just as the product of the original monodromies, and it's easily seen to take this general form here. So it's upper block diagonal. This means that it being upper block diagonal, it has an eigenstate. The eigenstate would be the vector 1, 0, which is the fundamental string. So the fundamental string encircling this general configuration will be taken back to itself. So it is consistent to encircle this configuration with a fundamental string. This therefore gives a PPS state. And this PPS state becomes massless when the 2 branes or the configuration En and the additional brane coalesce. So we get an enhancement because we get a new type of BPS state from this encircling string. And in fact, it turns out that the properties of this new type of massless BPS state are precisely such that it extends the original algebra, Lie algebra En, to the affine Lie algebra het En, or it's a Kac-Moody algebra. The roots, the simple roots, are now the original roots, together with the root associated with this string loop, encircling the total configuration. This is an imaginary root which has the properties that in the root lattice, its self-intersection is 0, and its intersection with all the alpha i's with all the simple roots is also 0. And these two properties are actually key for the discussion, and they are sufficient to show that the new object that one gets by this enhancement is actually an affine algebra. So these are rank 1 enhancements, and they are possible for the entire E series, so for E8, 7, and 6, but also for values smaller than 6 with these definitions. So, for example, for E3, one can enhance to the common extension, affine extension of A2 plus A1, and so on and so forth. And this also includes the possibility of starting with the 0 algebra and enhancing it to just the affine algebra het E0. These were the rank 1 enhancements. There are also the rank 2 enhancements. The monodromy analysis alone admits several options, but relevant for us is only this one. Namely, we can enhance, say, our het E8 further by addition of an extra brane, an A brane or 1,0 brane. In this case, one gets 2 types of extra junctions from that encircle the types of branes, the junction delta 1, delta 2. They are both squaring to 0, orthogonal on each other, and orthogonal on everything else. And in this way, one enhances, in fact, E8 to the double loop algebra het E9, which is the loop extension of affine het E9. So why am I telling you all this? This is showing us that there can be certain directions in the moduli space of the 7 branes which go beyond the usual ADE Lie algebras. So what's the physics interpretation? Which enhancements can occur? And how is this realized geometrically? So let me first give the general statement for the physics interpretation that we will then develop further. This imaginary root from the BPS state encircling the new configuration, in fact, does not give rise to a single BPS state, but to a tower of BPS states, namely to infinitely many BPS states, one per winding number n of z, n in z around the full configuration. So for delta 1, we get an entire BPS tower. For delta 2, we also get an entire BPS tower. And this follows from the fact that delta squared is 0. So this means that if one BPS, the one junction is a well-defined BPS state, then this is true also for n copies of it. And the interpretation is that the appearance of these towers of junctions or towers of states signals an infinite distance degeneration in the brane moduli space, quote unquote, in the sense with the caveats discussed. And in fact, these BPS towers, one per junction, are nothing but the KK modes, which are then associated with a dual decompactification in a dual frame. In the case where we have the affine series het En for n smaller or equal to 8, this signals a decompactification from 8 to 9 dimensions. And for the special case, this is a single special case of het E9, where we have a loop enhancement like shown here. We have a full decompactification from 80 to 10D because we have 2 KK modes. And in fact, the fact that these junctions in this case are orthogonal in each other signals that we have a decompactification on just a torus. And this interpretation, among others, will be backed up by the heterotic dual. So let's now try to see the appearance of these states now more hands-on in a directly geometric realization of these F-theory limits, of these complex structure limits in F-theory. Of course, the most general way to describe these elliptic K3s is as a Weierstrass model. So the physical compactification space is a rational curve. We have an elliptic vibration over it, which is given in Weierstrass form as reminded here. And F and G carry the information about the position of the 7 branes, and where that discriminant vanishes, this is where the 7 branes are located. And of course, we all know that the different type of enhancements of ADE type can be read off in the Kodara-Neron classification from the vanishing orders of F, G, and delta, which never goes beyond the value of E8, which is bigger than or equal 4, 5, and 10. Everything else beyond is non-minimal and does not appear in this list. But the claim is that also the values 4, 6, 4, 6, 12 or beyond in codimension 1, this is the key word here, should be included in the compactification of the moduli space. More precisely, these loop enhancements that we just recalled in the monodromy approach require the appearance of non-minimal fibers in codimension 1. And such non-minimal fibers in turn lead to a degeneration, the infinite distance degeneration of the K3, which can be tamed, can be made more tractable with the help of a sequence of blowups. This leads to a degeneration of K3 into a chain of intersecting components, the Kulikov degenerations, and our goal will be to read off the physics of these Kulikov degenerations and connect to this brane picture. So this is what we are now going to embark on. So to this end, let me first recall you of a few definitions. In mathematics, a one-parameter degeneration of K3 surfaces is a family of K3 surfaces, which is parameterized by one complex structure parameter U. So this we can think of the essential complex structure parameter that we are looking at. For simplicity, I look only at the one parameter families here. U takes values in at the disk. So this is in an open set in such a way that for values U not equal to 0, we have a smooth K3 surface, say XU1, XU2, and the degeneration occurs for U equal to 0. Now, in mathematics, one likes to combine this entire degeneration into a threefold. One thinks of a threefold whose fibers are the K3 surfaces and whose base is this parameter space, which is the open set D. So we have a threefold with fibers away from U equals 0, a smooth K3, and the central fiber is degenerate into the K3 that we are interested in. According to a well-known theorem, the semi-stable reduction theorem by Mumford, it is in fact possible to ensure by some operations that every such degeneration can in fact be brought into a semi-stable form. Semi-stable means that the central fiber is the union of a set of smooth surfaces, xi, for example, like here. They appear with multiplicity 1, so the whole situation is reduced. And the only singularities are the normal crossing singularities of these different components. This, the operations may include birational transformations on the threefold, which leave the fibers away from the degenerate one invariant, or a base change, so that's a change of parameter from U to the n, essentially. But from now on, we will therefore always be thinking about the semi-stable type of degeneration, because it can always be ensured by the operations just mentioned that we're in such a case. And another theorem, furthermore, guarantees that up to birational transformations in base change again, such a semi-stable K3 degeneration, Y, can always be arranged to have trivial canonical bundles. So the fibers, of course, have canonical bundle, but also the entire threefold can be guaranteed to have canonical bundle, vanishing trivial canonical bundle. And then we speak of a Kulikov model. And the reason why this is useful is because these Kulikov models enjoy a well-known classic classification into Kulikov models of type 1, type 2, and type 3. According to this classification in the mathematics, the Kulikov models of type 1 occur at finite distance. They are such that the central fiber is just a single smooth reduced surface. So for example, orbifold or ADE type singularities of K3, these are degenerations that would fall into this finite distance class type 1. Interesting for us, therefore, are the remaining cases, type 2 and type 3, because these occur at infinite distance in the moduli space. In type 2, we have in fact, the central fiber being a chain of surfaces, which now I call V0, V1 up to Vn, such that the end chains are rational surfaces, so birational to a P2, and the surfaces in the middle, if any, would be elliptic rule surfaces, so elliptically fibered, and there's also ruling. Details are not so important. What is important is that the intersection of two such surfaces is always an elliptic curve, a smooth elliptic curve of the same complex structure model, of the same complex structure everywhere. Kulikov models of type 3, this is the more complicated class, on the other hand, are degenerate into a union of such surfaces, each of them being rational, and the intersection of them being either zero or a rational curve. So the key point here to keep in mind, the difference is, in the type 2 case, we have an elliptic curve at the intersection, and in the type 3 case, we have a rational curve at the intersection, and this determines the difference. Now let's first look at the type 2 models to gain some intuition. It is known, as part of the theorems just cited, and the further developments, that in a type 2 model, we always find two transcendental two tori, which I call gamma I, gamma 1, gamma 2, whose calibrated volume in the limit, i.e. on x0, vanishes. And by calibrated volume, I mean the volume obtained by integrating the holomorphic 2,0 form over the transcendental 2 cycle. This already gives a hint at how the Swampland distance conjecture would work, at least at this level, namely if we consider M theory on such a family in the limit due to 0, it is clear that we expect two towers of asymptotically massless BPS states from M2 branes wrapping these transcendental 2 tori whose calibrated volume goes to 0. And since these are tori, we can wrap n times, this is a general feature, to get an entire tower of states. So per torus, we get two such, per torus, we got a tower, so we get two towers altogether. These states are there, so the Swampland distance conjecture would be happy, but in general, they will only be a subset of the asymptotically massless states, and it's important to analyze if there's more than that. So we need to understand in more detail beyond the statement what the origin of these two tori is and what the interpretation of the states is. In fact, for elliptic K3 surfaces, the E8 fibered elliptic K3 surfaces, the type 2 generations are of a rather canonical form. It was discussed in this paper that the compactification of this moduli space in fact corresponds to only two possible degenerations of type 2 type, so-called type 2A and type 2B. I'm using the notation of these papers here, so this has nothing to do, of course, with type 2A, type 2B string theory. In both cases, the K3 degenerates into two surfaces which intersect over a smooth elliptic curve. In the first case, type 2A, the two surfaces are DP9 surfaces. In the second case, there are P1 fibrations over P1, over the base, which again intersect over an elliptic curve. And the first class, of course, is known to string theorists from heterotic F-theory duality, and the second, in fact, from the Sen limit. So let's look at them in more detail. The first possibility, type 2A model, would be that of this that underlies the stable degeneration limit of F-theory, or in fact, which underlies F-theory heterotic duality. So the situation is that the K3 degenerates. This is well known, but let me now describe it from the point of view of what we would then generalize. The K3 degenerates into two DP9 surfaces. Each DP9 is an elliptic fibration over P1. We heard about this already in the talk of Cyril on Monday in a not unrelated context. So we have an I0 fibration over P1, a DP9 surface, with 12 singular fibers. This corresponds to the partition of the branes into 12 plus 12 branes. And they intersect over the common fiber. So this intersection curve is the elliptic fiber over the intersection point of the base. And now comes the important point. Where do the two tori come from whose volume vanishes in this degeneration limit? On the intersection curve, which is a torus, we have two 1 cycles, SA and SB. And we can think of fibering each of these 1 cycles over the vanishing 1 cycle, sigma, which vanishes at the intersection point, which can be pinched to this and taken to the intersection point. This gives rise to two tori, gamma 1 and gamma 2, one for SA and one for SB. And it is clear that the volume, intuitively clear that the volume vanishes because the sigma can be transported to the intersection point. And these are the two tori which are guaranteed on general grounds and which lead to the particle towers in the M-theory picture. But what is now the interpretation in F-theory? In F-theory, wrapping the M2 brane on the 1, 0 or 0, 1 cycle, of course, gives rise to either an F1 or D1 string, a 1,0 string or 0,1 string. And since we fiber this over the 1 cycle sigma, what we recover are, of course, precisely the string junctions, the delta 1, the 1,0 string, which encircles here all the 12 branes, or the 0,1 string, which encircles the 12 branes as well. So we have a configuration of two types of strings encircling the configuration of 12 branes, one on each of the two DP9s. And this should ring a bell. This is precisely what we saw in this double loop extension to hat E9. Namely, hat E9, as I recall, is the E8 enhanced by 2 more branes, so that altogether we have 12 branes. The total monodromy was 9 minus n, so this is a 1, 0, 0, 1. This is in fact the monodromy of the inverse of the monodromy of the fiber over the singular point. And the fact that these two tori exist is just a statement that we can encircle the full set of 12 branes because the monodromy leaves both the string 1, 0 and the string 0, 1 as one of its eigenvalues. So the hallmark of this is really a component with I0 fiber, the DP9, intersecting another component in an I0 fiber, so in the torus of type 2. And the physics, once more, will be that of an 80 to 10 d decompactification limit in the dual heterotic theory associated with this F theory, to which I will come in a second. So this was the type 2a picture. This has now clarified what the physical origin of the torus is, and I claim it also clarifies what the physics of the limit is. What about the type 2b? This is part of this classification. So please don't be confused now in my picture here. According to the classification, this is so the x0, excuse me, x0 now degenerates into x1 and x2. x1 is a p1 fibration over the base. x2 is another p1 fibration over the base. So here my first p1 is this line here, x1, that its vibration gives x1. The second p1 here, its vibration gives over p1b gives x2. These intersect in 2 points, but it turns out that these 2 points are exchanged due to monodromies, due to so-called type 3 fibers elsewhere. So this means that the intersection are not just 2 copies of the base, but 2 copies with this monodromy, in other words, a bisection. So these 2 components intersect out in a bisection, a ramified double cover of the base, which in fact is again a torus with 1 cycles sigma 1 times sigma 2. Now, in addition, since we can think of this entire degeneration as essentially 2 p1s in the fiber, we have one vanishing 1 cycle in each of these fibers. Let's call this the S1A fiber. This is what one gets in an I2 degeneration. And one can now combine the vanishing S1A fiber with one of these 2 1 cycles in the intersection sigma 1 or sigma 2. This again gives 2 vanishing 2 tori, but the vanishing now is only because of the vanishing of the S1A in the fiber, which is a consequence of the I2 degeneration. So which types of states does one get? As always, one gets the states from M theory by wrapping M2 brane on this 2 cycle. This gives the BPS states, and again we get 2 tori. So therefore 2 tori gamma I, and therefore 2 towers of states. And this gives rise to states, PPS states whose vanishing volume now here intuitively, whose mass in M theory units is proportional to the vanishing volume of the vanishing cycle S1A. But there's more at the leading level, namely we in addition have excitations of a non-BPS tensionless string from an M2 brane wrapping the vanishing 1 cycle in the fiber. This gives rise to a string, and the string tension squared is again given by the volume of this S1A. And it turns out that the interpretation of these 2 objects, the BPS objects given by the BPS particles and the tensionless string, is precisely as expected from the F theory point of view. Namely, these types of degenerations are realized in a Sen limit to weakly coupled type 2b orientifold. Recall we started with a situation where we have an I2 fiber. So this occurs when we take essentially the string coupling to 0 everywhere over the base. And we therefore get a type 2b orientifold description, the type 2b orientifold being defined precisely on the intersection curve E. And the asymptotically tensionless weakly coupled 1,0 string gives rise to a tower of states, just the fundamental string states in this type 2b perspective, which sits in type 2b units at the same order as the BPS particles. So the theory is that of 2 BPS towers, but in addition, a string tower, and therefore the decompactification is not an option, rather we get an effective 8-dimensional theory. So the lesson here is that we can classify the type 2 Kulikov models for the elliptic fibration into type 2A and type 2B. And this gives rise to two physically different scenarios, either the decompactification limit, which is a realization of the double loop algebra het E9, or an emergent string limit in 8 dimensions, which realizes the type 2B or Zen type limit. Okay, so this was for the type 2. Let me go back to the original slide so that you can orient yourself. This was the type 2 case. And now we come to the type 3 case, which is considerably more involved. It is generally known once more that there exist vanishing tori, but now the point is that there exists only one vanishing 2 torus, which are called gamma 1, whose calibrated volume goes to 0 in the limit. So we expect one tower of BPS particles from M2 branes by the same argument. So the classification of these type 3 limits is much more involved. But for starters, let me give you an idea of what can happen. The simplest scenario is that we have a degeneration into several components. And one of the components here, the end component, is again a DP9 surface, so an I0 fiber over a base, but such that it intersects another component with an IN fiber. So the two bases of these two degenerate fibrations intersect at a point P. And over this point, we have the intersection curve, and the intersection curve is the intersection of these two fibers. So in the present case, this would be an IN fiber. And I'm sketching here the non-blown up version of these IN fibers. One has to blow them all up. But in the non-blown up version, the IN fiber would look like this. So what would now be the origin of the massless torus, of the vanishing volume torus? We have a vanishing 1 cycle in the fiber SA. We can fiber it over sigma once more. And we can do so because the monodromy is precisely of the type that allows for this 2 cycle in the full fibration. This is not true for the corresponding SB fiber. That's why now, differently to before, we have only one type of 2 tori whose volume vanishes in the limit. And in the F-theory perspective, we can understand this because now on the DP9, away from the intersection point, we have only 12 minus n branes. These are now encircled by the string that we obtain by wrapping the M2 brane on the vanishing SA cycle. This is again the 1,0 cycle. And this is an eigenstate of the monodromy matrix of E hat 9 minus n, the affine extension. And the monodromy matrix is in fact the inverse of the monodromy matrix of the IN, which characterizes the intersection point. So this is the hallmark. We have a DP9, an I0 fibration, intersecting an IN fibration in an IN fiber. And then by these monodromy arguments, one can relate the vanishing torus, which is guaranteed on general grounds, to the wrapping or the wrapping of a 1,0 string around the brane configuration on the DP9. And this identifies the corresponding tower of states from M2 branes wrapping this torus with the tower of states that one gets from the FI node that enhances the branes on the DP9, in fact, to a hat E9 minus n. So the loop enhancement is now traced back directly to the geometry. And this will be a partial decompactification of the dual heterotic theorem. So more systematically, one can now try to classify what can occur. Recall, we are looking for complex structure degenerations compatible with the elliptic vibration. Therefore, all the degenerations at infinite distance must respect the elliptic vibration structure. So we can think of degenerations in codimension 0 and degenerations in codimension 1. Degenerations in codimension 0 can be argued, modular base change and rescalings of a Weierstrass model, always to lead at worst to degenerations of type IK over the entire base. And these are recoupling limits at infinite distance. So these give rise to Sen type limits. The interesting ones are the degeneration limits that occur in codimension 1 fibers. At finite distance, these are the usual ones that lead to ADE type singularities. At infinite distance, these require vanishing orders beyond the minimal Kodara bound. And in fact, unless the bound is strictly violated both for F, G, and delta in this Weierstrass model, we can prove that indeed, or we see explicitly, we can prove that a succession of blow-ups always leads to components, to fiber components with only IK fibers. So this is a generalization, what I just showed here, just with many, many components of IK fibers intersecting. If modulo blowdowns, all IK fibers are in fact of type I0, then we have a type 2 configuration. In fact, further blowdowns can take it to type 2A. This, we give explicitly the conditions for when this happens in the Weierstrass model. And this is the situation where we have 80 to 10 deconvectification. If modular blowdown, some of the IK fibers remain of IKK positive, then we have a type 3 degeneration. Again, this is when this can occur. And at least one of the IK component will intersect an IK plus N in such a way that on the IK component, we have an enhancement to het E9 minus N. This would be a generalization of the situation where both types are IK, but an IK intersects an IK plus N such that the same monodromy arguments go through. And in this way, we can systematically give the different cases, and they all fall to the extent that we understand it now into the scheme. I think my time is essentially up, but I would like to, do I still have 1 more minute?
Sure.
Okay,
yeah.
Thank you. I would like to briefly, very briefly show how this works in an example. This is not part of the classification, but this is the example. So for instance, if we start easiest case with an E7 times E8 Weierstrass model, E7 at say T equals 0, E8 at S equals 0, then we can wonder what does it take to analyze these, to arrive at these non-minimal degenerations in codimension 1. For instance, if we want the degeneration at T equals 0 in this example, then we would have to take C and D, these components, to 0 in a controlled way in terms of a parameter, which we can parameterize. And as it turns out, what will then be relevant is the vanishing behavior of the remaining components A and B. One can do this very systematically and in this way either obtain a type 2 limit, which is indeed after blowdowns a type 2A limit, or a type 3 limit precisely of the type that I advertised as a general feature. And from the resulting loop algebras and further enhancements, one can then also read off the gauge group after degeneration in the resulting 9-dimensional theory. In the 10-dimensional theory, of course, the gauge group is E8 times E8. So one can not only state that one finds a decompactification, but also say something about the model then in 9 dimensions, at least its gauge group. For example, if we take this parameter k equal to 0 here, then one sees one needs 4 blowups. We get DP9 surfaces, each with 12 branes on the 2 endpoints. This is precisely as giving rise to a het E9 configuration. The strings, the towers of states from both sides can be identified. In fact, the middle components, since they are trivial, can be blown down. So we're back in this type 2A situation. And the 2 towers that we get would then, as we claim, be the decompactifications towers to 10Ts. If we now systematically look at other vanishing orders, we realize type 3 models by intersecting also with IK fibers. In this case, for example, one would get an enhancement that to a het E8 and something that looks like het E8 also on this side, but in fact can be argued to give rise to gauge group E7 in 9 dimensions, and so on. And this is the last slide that I want to briefly mention. Namely, I mentioned several times that we have also the heterotic dual as a checkup on the physics interpretation. Precisely in this model, we can make this very explicit. Namely, these Weierstrass parameters A, B, C, D are known to map to Siegel modular forms, which are modular forms depending on the true complex, on the true moduli of the heterotic theory, the torus, complex structure, and Wilson line of the dual heterotic theory. By using the expansions for these Siegel modular forms together with their vanishing behavior in the limit, one can read off the behavior of, in particular, the complex structure on the torus on the heterotic side. And indeed, in this way, one can confirm that the type 2 cases indeed match a decompactification to 10 dimensions, and the type 3 cases match decompactification to 9 dimensions. And finally, I said we can, using this general picture, make general statements also about the actual theory after decompactification. So in particular, we can reproduce the known classification of maximal non-abelian gauge groups in 9 dimensions by systematically classifying the possible affine extensions which can occur in this framework, and trace back all the known maximum non-abelian non-abelian 9-dimensional series to these 2 types of combinations of affine branes. Okay, I'm sorry for going over time. Let me be very brief. We found further evidence or support for the emergent string conjecture now for the first time in the context of complex structure degenerations of F theory, in the sense that we take into account the, so to speak, open brane moduli spaces as well for F theory on K3. And we found that apart from recoupling limits, the non-trivial infinite distance limits lead to an affine or loop enhancement corresponding to a decompactification in agreement with an explicit analysis of the geometry of degenerations via Kulikov models. And once more, this gives a direct and explicit interpretation of the nature of the towers in the Swampland distance conjecture, and I think supports the claim that at the boundaries of quantum gravity, one indeed either finds a higher dimensional theory, a decompactification, or a weakly coupled dual string theory. Thank you very much for your attention.
Okay. Thank you very much for the nice talk. Any questions to Timo?
This conjecture you have at the top, what should I take as a quantum gravity actually mean? I mean, of course, we know string theory will give us quantum gravity, but I mean, suppose somebody want to prove this statement, where would I start? Because there is only one theory of quantum gravity as far as I know. And this conjecture makes a whole lot of sense.
Exactly. So this, of course, you're absolutely right. This is, of course, also the motivation behind this conjecture, and this is clearly what we see, for example, in when thinking about 10-dimensional string theories and their relation to theories in 11 dimensions, M theory in 11 dimensions. So two things: how to prove it without assuming anything about the origin of the, say, 4-dimensional quantum gravity theory. This is, of course, very difficult. Yeah. To prove it, you have to make some assumptions what your quantum gravity theory is. And but the statement is not vacuous. So you might think I start with the string theory, so it's clear that I get back a string theory. But this is not true, because what one has to show is that one can really identify a unique dual duality frame, or a unique duality frame which corresponds to a weakly coupled string. This is far not obvious. So if you think of, if I may go, if you think of this example that I started, this particular framework. So this is in the entire framework of F theory on on Calabi-Yau threefolds. So we start with a theory which is not actually described as a perturbative string theory in any way, F theory. So we could think of it as M theory on the Calabi-Yau fourfold in a particular type of limit. So no actual reference to a weakly coupled string is actually made in the definition of the theory, at least via M theory. And then by tracing back the structures of this of the limit in the geometry, one finds that asymptotic states arise as BPS states, in this case the strings, which define the new duality frame. Similar statements could then be made, for example, in M theory on Calabi-Yau threefolds or others. So even if we start with with frameworks of say M theory, where no reference directly to weakly coupled string is made, then still at the infinite distance limit of the moduli space, one can find such a new theory, a dual theory, without leaving the number of dimensions. So this would be the content, and it could have gone wrong in many ways. So it could, for example, have happened that rather than finding a unique dual weakly coupled string, one finds several strongly coupled strings which all compete with one another. And in fact, for a long time, this was a worry, and it was not clear how to exclude this. But by explicitly looking at the possible degeneration features of the internal geometry, it was then possible to see how this goes. So there's a lot of, in this case, Kähler geometry required in order to actually show this, that there are not competing strongly coupled strings, for example, which define the theory at infinity then. But I fully agree, proving this without making any assumption about what your four-dimensional quantum gravity theory is, I would not know.
Thank you.
And this, of course, is true for many of these conjectures, right? That in order to, yeah.
Any more questions? I don't see any more. So if not, let's thank Timo again for a nice talk. And I think at least we can finish the official part of this session. Thank you very much.